In Chapter 7, we are going to study kinematics and dynamics of circular motion. And once again, after this lecture, I'm going to record another lecture going through some examples of problems involving circular motion. First of all, let's start by defining what we mean by circular motion. If we have an object, say mass m, traveling around in a circular path as defined by this blue trajectory here. It's a circular path with radius r, and the velocity of the object is tangent to the circle as shown here in the diagram. So the green vectors, of course, are the velocity vectors, and the speed by which the object is moving around, if it's constant, i.e. the velocity vectors, if the velocity vectors have the same length, then we say that we have a uniform circular motion. So uniform circular motion when velocity, the magnitude of the velocity is constant, and it's a non-uniform circular motion when magnitude of the velocity is not constant, i.e. the speed by which the object moves around the circle changes. But in either case, the path is circular, so the path that the object follows is circular, i.e. r is always constant. So we're always dealing with a circular trajectory for circular path for the motion of the object. Now, in linear motion, we defined position by along either the x-axis or the y-axis. In circular motion, it's helpful to come up with a different coordinate system or different way of measuring position. Specifically, we measure position by what we call the angular position of the object. So in our xy coordinate system, as shown here in the diagram, in the xy coordinate system, let's say the initial position of the object is right here. So that's our initial position at ti, and the final position is up here. That's the final position at tf, and the time that it takes the object to travel from initial position to final position is delta t. Then of course we know tf is equal to ti plus delta t. That's trivial. Now the path linear distance that the object travels in this time, delta t, is the arc length s. This red path here is the arc length s. But let us now take a look at, let me change the color of my pen to green. If we now define the initial position of the object, now we know the object is always r, a distance r away from the origin of the coordinate system, where the origin is the center of the circular path. So we can now define the initial position by this angle here, theta I. So theta I is the initial angular position of the object, and theta F is the final angular position of the object, this larger angle here. Now we can talk in terms of delta theta as being the this angular displacement of the object over time delta t. So delta theta is theta f minus theta I. So delta theta is the angular displacement that the object goes through in time delta t. Now if we measure theta in radians and I advise you to keep your calculators in the radians mode from this chapter onwards. If we measure theta in radians, then the arc length S is given by this relationship. S is equal to r delta theta. Well, r is the radius of the circular path. So if you make a measurement of r in meters and delta theta in radians, then the arc length, if you multiply r by delta theta, then you get the arc length in meters. Now, just a quick refresher. As you know, I'm sure you've studied this in high school before, 360 degrees is equal to 2 pi radians. That's a simple conversion between degrees and radians. But if you keep your calculator in the radians mode, then you don't need to worry about the conversion. In case you're wondering what this omega is doing here, the omega is something I'm going to introduce in just a second, and we call that the angular velocity of the object. So our object, recall, had a linear velocity v, and omega is the angular analogous property of the object. Now, if the object makes one complete revolution around the circle is 2 pi radians. That's 360 degrees. So if the object makes one complete revolution around the circle in t seconds, this t is called the period. So t is the time that it takes for the object to make one complete revolution around the circle, the circular path. So we can come up with an expression for the magnitude of the velocity or the linear speed of the object by this expression. V is equal to 2 pi r over t, where t, as I said, is the period of the object, and we measure period, of course, in seconds. So once again, if you know the radius of the circular path, and if you know the period of motion, then you can calculate the linear speed of the object. Now let us go ahead and write our expression for the linear displacement in terms of angular displacement, linear displacement being the arc length s, and angular displacement, of course, is our delta theta. As we saw, the relationship is s is equal to r delta theta. Differentiating this expression with respect to time, we end up with ds dt is equal to dr dt delta theta plus r d delta theta dt. Now ds dt is the rate of change of linear displacement with time, which, as we have seen in previous chapters, is simply our linear velocity v. Now dr dt is the rate of change of the radius of the circular path, and as we said before, r remains constant, so this term is 0. So that whole term disappears. So we only end up with this term, r d delta theta dt. Now the d delta theta dt is the rate of change of angular position with time, and that's what we define as our angular velocity. So d delta theta dt is equal to angular velocity omega, and its units are radians per second. So from our s is equal to r delta theta, we now end up with another useful expression, which is linear velocity of the object v is equal to r omega. This is not a w, this is omega. Stands for angular velocity. So in the linear universe, we had linear displacement delta s, In angular or circular universe, we have delta theta, angular displacement. Linear universe, we had linear velocity v. Circular universe, we have angular velocity omega. So all the equations and all the tricks that you've learned for in the case of linear motion, you can now apply to circular motion. So if we have, for example, a plot of position, this is angular position versus time for an object undergoing circular motion. If you're interested in finding, let's say, the displacement of the object, actually let me back up. If you're interested in finding the angular velocity of the object, or at 2 seconds, for example, at this point right here, well, that's simply the slope of the line. The slope of position versus time plot gives you your velocity. So slope of angular position versus time gives you your angular velocity. So in this case, we have our omega is simply our final velocity is 6 pi minus 0 divided by 3 minus 0, which is 2 pi radians per second. So that's the angular velocity for the object at 2 seconds. Similarly, as you can see, in this region we have a negative slope, i.e. a negative angular velocity, and here we have 0 angular velocity. Similarly, if you know your angular velocity versus time plot, if you're interested in, let's say, figuring out the displacement of the object over 0 to 3 seconds, then what you do basically is take a look at actually 0 to 5 from 3 to 5 seconds. You look at the area under the curve from 3 to 5 seconds, which is this expression here, and the area under the curve there is minus pi times 2, which is negative 2 pi radians. So that's the displacement of the object between 3 seconds and 5 seconds. That's the angular displacement of the object between 3 and 5 seconds. So these tricks as far as the slope of let's say velocity versus time giving you the acceleration also applies. So if you know your angular velocity versus time, over here of course our angular acceleration would be 0 because it's a flat line, and the areas under the curve, the area under the curve rule that we learned for linear motion also apply. So there's tremendous amount of analogy between linear and circular motion. In linear motion we have final position is equal to initial position plus velocity times delta t. In the angular world we have final angular position equals initial angular position plus angular velocity times delta t. Right? And we know that v speed is equal to r omega, so that kind of connects the linear and angular entities to each other. Similarly, we had s is equal to r delta theta. Right? Now, in certain problems you have to convert back and forth between radians per second to revolutions per second or revolutions per minute, depending on what the problem is after. As I said, the units for omega are in radians per second. If you need to convert that to revolutions per second, just remember that there are 2 pi radians per revolution. So 50 radians per second is simply 50 divided by 2 pi revolutions per second. Similarly, if you have 8000 RPM, that's revolutions per minute, RPM. So if you have 8000 RPM and you want to convert that to radians per second, so 8000 RPM is expresses an angular velocity. So there are 2 pi radians per revolution, and there are 60 seconds per minute, so you multiply by 2 pi, divide by 60, and whatever that number gives you, that's our angular velocity in radians per second. So in most of the problems you have to convert back and forth between such units. Now, one thing I like to say is that that's the main difference between what we learned in linear motion and treating linear motion and circular motion, is that in linear motion you had the luxury to choose which way was positive and which way was negative. We said that you can choose your coordinate system such that, let's say, to the right of the origin was positive, to the left was negative, or to the y was positive up from the origin and negative down from the origin. In circular motion, you don't have that freedom. It is predefined for us. The convention is that in circular motion, if an object is moving counterclockwise, then we say that the angular displacement is positive. Alright, similarly your angular velocity is positive. Alright, and if it's moving clockwise, then we have a negative for these quantities. So anything which is counterclockwise is positive, anything which is clockwise is negative, counterclockwise is positive. So clockwise is negative, counterclockwise is positive. Okay, so that's about the only main difference between dealing with linear and circular motions. So think about this question for a couple of minutes and I'll give you the answers if you got it right. So we have a particle moving clockwise around the circle at constant speed for 2 seconds. It then reverses direction and moves counterclockwise at half the original speed until it's traveled through the same angle. Which is the particle's angle versus time graph? So think about it for a minute. You may want to put the video on pause so you can think about it, and then I'll give you the answer. Okay, now pay attention to a couple of things here. First of all, we know that the particle travels through the same angle. Therefore, we know that the angular displacement of the particle, delta theta, is 0. So that rules out option A, because angular displacement is not 0, and option C. So we only have B and D to consider. Now we're told that the particle moves clockwise. So initially the particle is moving clockwise, and clockwise is a negative angular or negative displacement to start with. As I said just a minute ago, anything clockwise is negative in circular motion. So as you see, B is the one that has a negative angular displacement, angular velocity to start with. and then it gets less and less negative as time goes by, i.e. It's a positive displacement indicating a counterclockwise displacement after, let's say, this 2 seconds. And the slopes of these these lines, the slope between, let's say, 0 and 2 seconds in the first phase is, as you can see, twice as much as the slope of the second part, which is consistent with this half the original speed piece of information that we have. Also, the fact that we have two straight line segments for phase 1 and phase 2 is consistent with the constant speed. So B is the correct answer. So I hope you got this right. Now let me introduce the RTZ coordinate system. RTZ coordinate system is what we make use of in studying circular motion. This is a coordinate system where you can imagine the coordinate system being kind of stuck onto the object as it moves around in the circular path. And the R coordinate, let me change the color of my pen, the R coordinate always points towards the center of the circle. So if the object were here, then the R coordinate would be like this. Alright. The T coordinate is always tangential to the circular path and points in the direction that the object is moving. Alright, so that's our T coordinate when the object is here, and that's our T coordinate when the object is here. And the Z coordinate is perpendicular upwards. Alright, and if you use what we call the right hand rule, so if you kind of stick out your right hand, if this is your thumb and this is your index finger, and this would be your middle finger, and then the other two would kind of be folded like this. Right, I apologize for my terrible drawing here, but that's the best I can do. So your index finger is the T coordinate, R is your middle finger, and Z coordinate is your thumb pointing upwards. So that's one way to remember which way the coordinate system points. Okay, but make sure you always use your right hand. So that's why it's called the right hand rule. Alright, so in the RTZ coordinate system, let's say if you want to show the components of a vector A, here A is just any old vector. So remember, the origin of the coordinate system is where the object is, right here, and the T is tangential to the circular path, so AT, which is the T coordinate, the T component of A, is tangential to the circle. AR is along the radial direction, and the Z is out of the page, is pointing directly at you. In the problems that we'll be dealing with, we are not going to consider yet any components sticking out of the page or into the page. So let's just focus on the T and the R components for the time being. Now, it is customary to define the angle that A makes with the RTZ coordinate system using symbol phi, and it's always given with respect to the radial axis. That's customary. I'm not saying you have to do that, but that's what is done most commonly. It's the angle phi is typically given with respect to the radial coordinate. So using phi, then you can decompose A into the AT and AR components as given, and as I said, AZ in this case is simply 0. So that's how you would decompose any vector in the RTZ coordinate system. So here let's take a look at our object once again, moving around at constant speed around a circular path. It's constant speed, which means the magnitude of the velocity vector v is the same at all points. However, its direction changes, which means that there is an acceleration acting on the object. And if you, the book in chapter 7, the book gives you a simple geometric argument why this acceleration vector a always points towards the center of the circle. I won't go through its proof here. Later on in chapter 13 we'll do much better proof of it, I hope. But please do take a look at the chapter and convince yourselves that a must always point towards the center of the circle. That's why we say that for an object to have a circular path, there must always be a radial acceleration acting on the object. So the object must have radial acceleration. Now it is an acceleration, so it has units of meters per second squared. It's linear. As it's linear because it always points towards the center of the circle, and its magnitude, I'll just give it to you here, and then, as I said, we'll prove it in chapter 13 when we do rotational motion, is equal to v squared over r. So the magnitude of the circular of the radial acceleration is equal to square of the speed of the object divided by r, which is the radius of the circular path. AR is equal to v squared over r. It's a very important relationship for you to remember or have on your equation sheets come exam time. Now Newton's laws, in particular the second law, is equally applicable in the case of circular motion as it was in linear motion. So we can say that the sum of the forces along the radial direction must equal mass times acceleration along the radial motion, and we just said that AR is equal to v squared over r, so which we can substitute v squared over r here. So sum of the forces along the radial direction is equal to mv squared over r. That's the equation that you'd be using all the time in solving problems involving circular motion. Now in uniform circular motion, we said v is constant, therefore the sum of the forces along the tangential direction is equal to 0, and sum of the forces along the z direction is equal to 0, because we only have acceleration in the r direction, the radial direction. Now in non-uniform, change the color of my pen, in non-uniform circular motion v is not constant, and in that case ft is not equal to 0. In fact, sum of the forces along the t direction is equal to mass times some acceleration in the t direction. Remember, the non-uniform circular motion was one where the speed of the object varied with time. So here we have the speed of the object is yay long at position 1, less in position 2, and even lesser in position 3. So we go from big to small to smaller, going around the circle and then back again. So obviously for this change to happen, we need a component along the tangential direction. Recall the tangential direction was tangential, of course, to the circular path, and our velocity vector is always perpendicular to the circular path. Is always tangential. I'm sorry, tangential to the circular path. So for this velocity magnitude to change, for the speed of the object to change, then we require an acceleration in the tangential direction, i.e. AT is non-zero, which means that the sum of the forces in the tangential direction must not be zero. But whether we are dealing with uniform or non-uniform circular motion, the sum of the force along the z direction is always zero. Okay, so let me ask you this question, and I'll summarize what I just said in just a second. So if you have, think about this for a second, and I'll give you the answer. If you have a uniform circular motion, so the key word here is uniform, and also circular, of course, the net force always points towards the center of the circle, points towards the outside of the circle, its tangent to the circle is zero, depends on the situation. So what do you think the answer is? And I hope all of you chose A. It always points towards the center of the circle. Now if we had a non-uniform circular motion, what then? Well, we know that in non-uniform circular motion we must have a component AR pointing towards the center of the circle at all times. Alright? So AR would be pointing towards the center of the circle, but we would also have AT, a tangential component. Alright? So the net acceleration would then be a vector kind of which points at an angle away from the circle. I can show this graphically better down here. I'll come back to these in just a second. So let me show it here. So in a uniform circular motion, the acceleration vector is simply AR. It points towards the center, it's along the radial direction. But in non-uniform circular motion, we have both AR and AT. So the net acceleration A is made up of the components along the tangential coordinate and the radial coordinate. So and it doesn't necessarily remain the same, of course, throughout. But in both cases, the important thing is that the path of the object remains circular. Very important to remember that. This is circular motion. So this AT that we talked about, the acceleration along the tangential axis T, as you know, this is AT is along this axis, which means that there is a net force F acting in the tangential direction. That's why it changes the magnitude of V, the speed of the object. And once again, you take it from me for the time being, and then we'll prove it rigorously in chapter 13. AT is given as R alpha. Well, R is our familiar radius of the circular path, and alpha is what we call angular acceleration. Angular acceleration. So once again, alpha, when alpha is 0, that means we have 0 angular acceleration, or we have a uniform circular motion. And of course, when alpha is non-zero, then we have a non-uniform angular acceleration. Okay. Now, in dealing with dynamics of circular motion, once again we do a nice pictorial representation. Here we have a dad swirling the kid around in a cart. The kid's speed is V, and the radius of the circular path is R. We know that the mass of the kid on the cart is 25 kilograms. Radius is 2 meters. The tension in the rope is 100 newtons. So tension, of course, is the force in the radial direction. So that's Fr. So our tension is Fr here. Okay. Find omega in RPM. So doing our free body diagram on the right hand side, you need to, well, first of all, your free body diagram is going to be in the using the RTZ coordinate system. Okay, so where's the object? Object is here, and the R coordinate is points to the left, so that's exactly what you do. The origin, remember, is where the object is, and your R coordinate is pointing to the right. Did I say to the left before? I apologize. So the object is here and the R coordinate is pointing to the right. So you choose your R coordinate pointing to the right in doing your free body diagram. Okay. Now, looking at the kit from this angle, kind of you're level with the road, and looking at the kit from this angle, then the Z coordinate is pointing up, and then you draw all the forces acting on the object. Well, you have tension in the rope pointing along the R direction, you have weight pointing down, and you have normal force from the road or the surface pointing in the positive Z direction. Now we know that the sum of the forces in the Z direction is always 0, so that tells us that omega must equal n. We don't need this piece of information to solve this problem, but when we deal with friction involving circular motion, then it's the important piece of information that you need to resolve, of course. Now, and sum of the forces along the radial direction must equal mass times acceleration in the radial direction. Well, acceleration in the radial direction is equal to v squared over r, so that's mv squared over r. Okay. And sum of the forces in the radial direction is simply T, tension, is equal to mass v squared over r. What did we say v was equal to? If you recall, v was equal to r omega, right? Where was it? Way up here somewhere. There we go. V is equal to r omega. Alright. So using v is equal to r omega. Where's the dad and the kid? There we go. We end up with v. T is 100 newtons, so 100 newtons is equal to mass times omega squared r squared divided by r, which is mr omega squared. Okay, so m is 25 kilograms, r is 2, we know tension, so now you can calculate what omega is simply, just plug in the numbers. Okay, so in doing analysis like this, once again, we did a pictorial representation, free body diagram, used Newton's equation, F equals ma, and made use of v equals r omega, and ar is equal to v squared over r. The two equations that I said are very important to note on the side of your equation sheet. These are the ones that you'll be using all the time in solving these problems. Okay, now going back to what we said a minute ago as far as non-uniform circular motion, now the acceleration vector a here that was made up of the radial component and the tangential component, vectorially, that's a vectorial equation for it, of course. A is equal to at plus ar. Now its magnitude is given, can be found using the Pythagorean relationship in this form, and of course the angle phi that it makes with respect to the radial axis is simply arctan of at over ar. Alright, these are These are the stuff that we've covered before, so I won't dwell too much on it. Now, here what I'm showing is a ball going around a circular path of radius r, let's say, going around the circular path in it's a roulette ball. Okay, so roulette ball kind of going round and round. Now, in the case of the dad and the kid and the cart being connected by a rope, the net radial force was supplied by the tension in the rope. But here you have to be a little bit more careful in deciding where the radial force, the net radial force, is coming from. Now, this radial force that we talk about is not real force per se, it's a net force. So you have to identify real forces acting on the object and then decide which ones contribute to this net radial force, giving rise to radial acceleration, which results in a circular motion. So if we were to identify real forces acting on this object, well, what do we have? We have, of course, its weight, and then we have a normal force acting on the object from the bottom surface here. Then what other forces do we have? The ball is also in touch with the side surface, so we also have a normal force due to this side surface here, alright? And of course we have some friction forces. There's a friction force tangential to the side surface. There's also a friction force tangential to the bottom surface. Okay, so if you were to look at all these forces, the only force that has a component pointing towards the center of the circle at any time is the normal force from the side wall. So if the ball were well, actually, if I draw a bird's eye view, so that's the tray, whatever, and here's the ball, that's the center of the circle. The normal force from the side wall points towards the center at all times, whereas the friction force, of course, points, if the ball is moving this way, if the ball is moving counterclockwise, then the friction force, of course, points along the tangent, but in the tangential direction, but the negative t direction. So the friction forces don't contribute. The weight, of course, doesn't contribute. The normal force from the bottom wall doesn't contribute. So it's a normal force from the side wall that is the only force that contributes to the ball moving around in a circular path. So the first task that you need to master in solving circular motion, problems involving circular motion, is having identified all the forces that act on an object, decide which ones make up this net force, or the sum of the force and the radius, or this net force Fr net. Net force along the radial direction, because when you figure that out, then you know that net force along the radial direction divided by mass of the object is going to give you your radial acceleration, which is equal to v squared over r, and you're more than halfway home by then. So the most difficult part in these problems is being able to figure out which forces contribute to the radial force. So if you miss one, then of course it's very difficult to get the correct answer at the end of the day. So in this example, and as I said before, I'll be giving you examples in the next lecture. We will walk through examples of a few problems. So in this example, we have an object M which is being moved in a circular path. It's tied to a string, 1 meter long string. The pivot point is here, so that's point of support, and the circular path is indicated by the blue circle. Now as you can see, it's a clockwise rotation. So just as a side note, our angular displacement is negative in this case, and our angular velocity is negative, but we don't need to know that to solve this problem. I just wanted to mention that for sake of giving you a piece of information, that's all. So the radial distance is r. Once again, our relationship is AR is equal to v squared over r. Now v in this case is the velocity or the speed of the object, which is tangential to the circular path. Newton's law applies. Now in this case, what you need to ask yourselves is that what force has a component, or which forces have components along the radial direction, because after all we want to end up with a net force in the radial direction, because we know the object is moving around in a circular path. So if you were to look at all the forces acting on the object, well, what are they? Well, we have the tension in the string, and we also have the weight of the object acting down directly. W and R are orthogonal, so obviously weight cannot contribute anything in the radial direction. So the tension is the only force that may have a component or has a component in the radial direction. And if this angle were phi, then net force along the radial direction is simply tension cosine phi, and that's equal to mv squared over r. And from there you can go about solving a problem like this. In the z direction, we know Fz is equal to naught, because as I said, in circular motion, whether uniform or non-uniform, this is always true. So in the z direction, then Tz is t sine phi, and w is down towards the negative z direction, so minus w is equal to 0. So we can figure out, now we have two equations. One is t sine phi is equal to w, which is mg, and the other equation from up here gives us t cosine phi is mv squared over r. Now dividing these two equations, we end up canceling out t, which was an unknown. We didn't know what the tension was, so we end up with tan phi is equal to gr v squared. So if you know the speed by which the object is moving around the circle, then you can figure out what the angle phi is, or vice versa. If you had the problem giving you phi, the angle that the string makes with the plane of the motion, then you can figure out what the speed of the object is, etc. Let me walk through one final example here. Now I've shown our car. Let me switch the color of my pen. In three situations, A, B, and C. A is when the car is moving along the horizontal surface. B is when it is moving in a dip. It's a dip of 200 meter radius. And then situation C is when it's going over a hill of a 200 meter radius. Okay. So the analysis for scenario A is just the way we've done so far. So if we call this direction X, then our free body diagram is shown down here. Alright. So we have weight of the car pointing down, normal force pointing up, and there's some friction force in the reverse direction as the motion of the vehicle. The speed of the car is v forward. So sum of the forces along the y gives you n is equal to w mg, and sum of the forces along the x direction is equal to minus w mu k, where mu k is the coefficient of kinetic friction. So you can figure out ax, which is the acceleration in the x direction, which is equal to minus g mu k. That's using those two equations. Okay. Now the question is, how does this acceleration along the motion of the car change when in scenarios B and C? So scenario A gives us ax, which is the acceleration of the object. As you can see, it's a negative value, and that's doing our sanity check, that holds, because of course if you're not applying any gas, then one would expect the car to slow down. It's a negative acceleration, and its magnitude is depends on the coefficient of friction, which is also makes good common sense. Now in scenario B, when we are going kind of in this dip region here, then it's a circular motion at that point at the bottom of the dip. So we use our RTZ coordinate. Once again, notice that if the car is at the bottom of the dip there, then the R coordinate is pointing up towards the center of the circle, and T direction of course is tangential to the motion at that point, okay, which is horizontal in this case. So now our forces remain the same. Still we have W, our weight, our normal force, and friction force, but now our coordinate systems are different. So let's write the Newton's laws. Sum of the force in the T direction is simply minus Fk, which is equal to minus N mu k, right? That really doesn't change. And sum of the forces in the R direction is N minus W, which is MAR. Now AR we know is equal to V squared over R, and using these two equations and doing some simple algebra, you end up with AT, which is acceleration along the tangential axis, or the linear acceleration of the object, is being given as minus G plus V squared over R mu k. So if you compare these two relationships, you see that the acceleration of the object is more negative when the car is going in a dip than when it's moving along the horizontal. Once again, that makes common sense. You'd expect to slow down more quickly, I guess, if you're kind of going in a dip rather than a horizontal surface. Now for scenario C, doing a similar analysis, now notice my radial axis is now pointing down, because on my pictorial representation R is downwards, T is still to the right. My forces haven't changed, they're the same. Alright, and doing the similar analysis, I'll leave it to you to work through the math here. You end up with the tangential acceleration is given minus G minus V squared over R into mu k. So comparing this acceleration and the original acceleration for the horizontal surface, you see that in scenario C we have a smaller negative acceleration, i.e. your car would slow down at a slower rate. And sure enough, you're going over a hill, if you let go of your gas, you're not gonna slow down as fast as you would if you're on a horizontal surface. So the sanity checks hold in both cases. So just an example of how to go about doing dynamics analysis in circular motion. In the next lecture I'm going to work through some specific problems. So let me stop this lecture right here and we'll carry on shortly.